Hey everybody. Today we're constructing confidence intervals for proportions. Oftentimes, we encounter random processes that have exactly two possible outcomes, like heads or tails, yes or no, or true and false. We'd like to be able to draw conclusions about the probabilities of those outcomes just based on sample data. We'll call one of the outcomes a success and encode it with a 1, and call the other one a failure and encode it with a 0. Here, success and failure are just technical terms, they're arbitrary choices, they're not intended to be value judgments on the different outcomes. When we encode our variable this way, we have a discrete random variable, let's call it x, with this probability distribution. X can take on two values, 1 and 0, with probabilities p and 1 minus p respectively, where p is just the probability of success. We call a probability experiment like this a Bernoulli trial. For instance, if you roll a standard 6-sided die and consider a 6 to be a success, you have a Bernoulli trial with p equals 1/6. We can compute summary information for this kind of random variable just in the usual way. The mean, or expected value, is the sum of all the possible values of the random variable weighted by their respective probabilities. For a Bernoulli trial, the mean is p. The standard deviation of a random variable is the square root of the sum of the squares of the differences between all the individual values and the expected value, each weighted by the probability of the individual value. The standard deviation for a Bernoulli trial is the square root of p times 1 minus p. Remember, the expected value represents the proportion of successes you should expect in the long run, and the standard deviation is giving you a measure of the variability of those results. So if you did Bernoulli trials over and over and over again, what kind of variability could you expect? Now let's suppose that we run n identical, independent Bernoulli trials, so p is not changing from trial to trial. The proportion of successes is given by p hat equals 1 over n times the sum of all the xi. So remember, xi is a 1 if you have a success, and a 0 if you have a failure. So that sum of the xi is just the number of successes in the n trials. And so p hat is the proportion of successes in those n trials. In particular, however, this is just a sample mean, and we can apply all of our knowledge about sampling means to p hat. The mean of p hat is going to be p, the same as the mean for an individual Bernoulli trial. And the standard deviation of p hat is going to be the square root of p times 1 minus p over n. So that's the standard deviation of a single Bernoulli trial divided by the square root of n. Moreover, by the central limit theorem, the sampling distribution of p hat is going to be approximately normal when n is large. And in general, 30 is more than enough. All right, now let's talk about confidence intervals. Remember, the basic structure of a confidence interval for the mean is mu equals x bar plus or minus z star sigma sub x bar. So here mu is the population mean that we're trying to estimate. X bar is the sample mean. Z star is a critical z value corresponding to the level of confidence. And sigma sub x bar is the standard deviation of the sample mean. So in this case, instead of x bar, we have p hat. And instead of sigma sub x bar, we have sigma sub p hat. So here's our formula for the confidence interval for a proportion. P equals p hat plus or minus z star square root p hat times 1 minus p hat over n. Now, if you're paying close attention, you'll notice that in that margin of error on the far right, I've replaced p with p hat. Remember, p is the overall probability of success on a given trial, the thing we're trying to estimate. P hat is the experimental proportion of success, so the proportion of successes in our sample. So p hat is the only thing we know. One other important observation here. The margin of error there on the right, z star square root p hat times 1 minus p hat over n, approaches 0 when the sample proportion is very near 0 or 1. So the first conclusion that we can draw from this is that we shouldn't use this sort of confidence interval in cases like that, when p hat is very close to 0 or 1. There are other techniques that we can use that we can study in more sophisticated statistics courses. As a general rule of thumb, you should only use this sort of confidence interval when you have a sample that has at least 5 successes and 5 failures. Here's an example. Researchers wish to determine what proportions of Americans own a dog. They contact 250 people at random, finding 116 that do own a dog. Construct a level 95% confidence interval for the population proportion. So we're going to use this formula, p equals p hat plus or minus z star square root p hat 1 minus p hat over n, where p hat is 116 over 250, or about 46%. The z star corresponding to 95% confidence is 1.960, and of course n is going to be 250 here. Plugging all of these values in, we get this confidence interval, 0.464 plus or minus 0.062. So the margin of error in this study is about 6 percentage points in either direction. Suppose we need a smaller margin of error, E. How large a sample do we need? This is a common and very important question in study design. So we have a formula for the margin of error, z star times the square root of p hat times 1 minus p hat over n. Here we know what E is supposed to be. We'd like to determine n. So let's just solve this formula for n. N equals p hat times 1 minus p hat times z star squared over epsilon squared. Here I've rewritten capital E as epsilon. So this is a very simple formula, but there's one small subtlety. We want to do this sort of calculation before we do the study, so before we actually know what p hat is. There's 2 ways around this difficulty. First of all, we might have some preliminary data, maybe a smaller study or a previous study that we can use as a legitimate valid estimate for p hat. If we don't have data coming in, we'll just go with the most conservative possibility. That is, the value that gives us the largest possible sample size over all possible values of p hat between 0 and 1. And that happens to be p hat equals 1/2, as we can prove using calculus, for instance. When you use that conservative estimate, you get that n is z star squared over 4 epsilon squared. And that's a formula that you really can plug into. Let's see an example. How large a sample is required to conduct a survey with 95% confidence if the margin of error can be no larger than 3%? In this case, we have no preliminary data with which to estimate p hat. So we're just going to use that conservative estimate, p hat, that last formula at the bottom of the last slide. Plugging in the values, z star equals 1.96 and p hat equals 1/2, and a margin of error of 0.03, we get an n of 1067.1. Final thing to say here is that, of course, a sample size must be an integer. We can't actually survey 1067 and 1/10 people. So we need to round this. In particular, we should always round the sample size we need for a specific margin of error up. Rounding up decreases the margin of error, while rounding down decreases it. And we need to make sure that our margin of error E does not exceed 3%.